Dear friends, Maths Aspirants is a community of mathematics students, research scholars, and teachers across India. And we used to arrange several online problem solving sessions to help the students who prepare for different national level competitive examinations in higher mathematics. As a part of this, today we have a session on functions of one real variable, and we have Mr. Vishnu Raveendran is with us to engage the session. Vishnu is now a research scholar in Karlstad University, Sweden. Uh, Vishnu completed his MSc from Tata Institute of Fundamental Research, Bangalore. I express my sincere gratitude and love to Vishnu for being with us. I welcome everyone to this program. Welcome, Vishnu.
First of all, thank you very much for inviting me to talk about some maths to these young students. And I'm very happy that like last year we have very great result due to this group. I hope like this year also we have the better results compared to last. So today I will mainly focus on problems on continuous functions, and if we have time, like I will move to some problems to differentiable functions also. So my plan is that like in the beginning, like we will recall some important results and some definitions which we need to solve the problems. Then we will start to solving the problem, and the problems are mainly theoretical problems, and it'll be kind of a state true or false type of question and give the reasoning. And it's very good like if you can participate the discussion and give some comments, because I may make some mistakes also, and it's I'm very happy if you can point out what I'm making the mistakes, and I'm sure like many of you are better than me in this particular topic, surely. So let's start. Let me share my hand cam. So let's start with continuous functions. We recall some definitions and theorems from this concept. So let's start from the definition of the continuous function. Let f from a subset of R to R, we say continuous functions if for any epsilon greater than 0, there exists a delta greater than 0 such that f of x minus okay, so first we will say the continuity at a point. So we say f is continuous function at point C. At point C, then f of x minus f of c less than epsilon if x minus c less than delta. So one way to understand this idea is that, for example, if you have a functions like this, and you're saying this is your point C, and we say this function continues at point C, then what it means geometrically is that if you take the point f of c, which will be here somewhere, and if you take any neighborhood around this point, f of c, so if you have an epsilon neighborhood around this point f of c, you can always find a delta neighborhood around the point C, such that if you take any point inside this delta, for example, if you take any x from here, and then f of x will lies between this interval. So just to understand the idea in a geometrical way. So this is the definition of continuous function at a point C, and if f is continuous, I'll use CTS for continuous function from now on. So if f is continuous at every point C element of A, then we say f is continuous on A. So this is the standard definition for the continuous functions. Now we discuss some other equivalent definition for continuous functions. So we discussed two equivalent conditions. One is that we say f is continuous at C if and only if limit x tends to C, f of x equal to f of C. So this is one equivalent definition. And we have a similar definition by using the sequence of real numbers. So we say f is continuous at a point C if and only if let xn be a sequence such that xn converges to C. Then f of xn, the sequence f of xn, also converges to f of C. So if we have any of this condition, we can say f is continuous. And this sequential criteria for continuity, this is we can use for to it's if you want to prove a function which is not a continuous, then I would say this is the one of the easiest way to prove. You find a sequence. So for example, if you want to prove f is not continuous at C, then the one of the easiest ways is that find a sequence such that xn converges to C and prove the f of xn not converging to f of C. So this is one of the standard method to prove f is not continuous at a point. Yes. So is there any question until now?
Okay.
No, then yeah, and one important example I would say to a function that is discontinuous at every point. So it's always better to remember this example. So can anybody tell me that there is a function that is discontinuous at every point from real number to real number?
Sir, it is 1 at every rational point and 0 at every irrational point.
Yeah, exactly.
Dirichlet
So,
function.
yeah, exactly. Dirichlet function. So Q, I mean rational number. Okay, let me image. So we define f of x equal to 1 at rational number or 0 or some other number, for example, -1 at irrational number, Q complement. So this function will be does not have a continuous point at the whole R. Okay. So now some of the important theorems. I will not discuss the proof of the theorem, but we need the statements to do the problem. So one is maximum minimum theorem. What it says that like if f is defined on a closed and bounded interval and it's continuous, then f has absolute maximum and absolute minimum on AB. So it's always important to remember that to satisfy the maximum minimum theorem, we need a compact set. I mean, like, we need a closed and bounded set. Otherwise, always you can find some counterexample, such as you define f from 0 to 1 to a f of x equal to 1 by x. So this function does not satisfy maximum minimum condition. Okay, so now let's look into other theorem, which is intermediate value theorem. So what it says that if I be an interval and f is defined from I to R, be continuous function, and if there exists a number k such that f of okay, so we define I is equal to some AB. Okay, f of A less than k less than f of B, then there exists one number C between AB such that f of C is equal to k. So this is very, I would say, one of the important theorem in continuous function. And if you look to some,
Sir, I is a closed interval a comma b.
no, I can be open interval also, or
F of a not equal.
yeah. Sorry, yes, I understand. Or I can be any interval and A and B element of I. That also work here. So I will be any interval. So I'll just picture this. So for example, like so your I start from C to D, and A and B are some point in I. So this is your I, and A and B are some point in I. Okay. So this is your f of A, and for example, this is your f of B. Then what the theorem says that if you have a number k between A and B, such that if k is between f of A and f of B, then you can always find a C between A and B such that f of C is equal to k. That's what the theorem says. Is it okay?
Yes, sir.
Yeah. Okay, so
Sir, 2C are similar points.
sorry, what?
Closed interval C, D, and there exists a point C, open interval A, B. And 2C are same. It is different. It should be C point.
So sorry, I did not get the point. So can you repeat, please?
The closed interval C, D.
Okay.
DC, and between A, B, this is same. So I say that this is different.
No, actually, you don't need to care about these endpoints. So the only thing is that your A and B should be inside the interval I. I mean,
Okay,
like
okay.
f of A and f of B should exist. Or if you have, like, for example,
Vishnu,
those, yes.
Vishnu, she is actually telling that you have chosen the same C to denote the in-between point as well as the
Okay.
interval. That's
Yeah.
why.
That's my mistake. So, yeah. Sorry. Yeah. So you can take C tilde. Yes. Yeah. Sorry for that.
Hello, sir.
Yes.
Sir, what is connection between continuity or intermediate value property? It always satisfy hold, or if continuous then also hold.
No, F should continuous. Like, for example, you can consider the functions like f of x equal to let's consider -1, f of x equal to 1 if x greater than or equal to 0, and -1 if x less than 0. So a function like this, okay? So this is not continuous. And what intermediate value theorem says that if you take your 1 point is 1 here and -1 here. So f of 1 is 1 and f of -1 is -1 here. So if the intermediate value theorem satisfies, then if you choose a number between that, for example, 0 is between f of 1 and f of -1, right? So there should exist a C tilde in the R, or this some interval here, such that f of C tilde is equal to 0. But in this function, you cannot find a C tilde satisfying f of C tilde equal to 0, because all the values of the function is 1 and -1. So the continuity plays an important role here for the intermediate value theorem. So f must be continuous.
Yes, continuity is necessary condition.
Yes.
But as I know, sir, it is sufficient. Maybe.
Sufficient condition, I'm not sure.
Okay, sir,
So you're saying, like, if f is satisfying intermediate value property,
then f need not be continuous function.
f is continuous or not. This I don't know how to do that. So anybody know any example which is a counterexample for this argument? So I'm not sure, like, what will be the condition if f is intermediate value property, then f is continuous or not. Yeah, that's a good question, actually. I don't know. Maybe I'll check and update. Yeah, but that's a
This
nice
is
question.
not true, sir.
Not true. So can you give me an example? So we
Sir,
can.
example, if fx equal to x, 0 to 1, 0 less than x less or equal to 1, 3 minus x, 1 less than x less than 2.
3
Yes, sir,
minus
this
x on where?
example. 1 to 2.
1 to 2. 1 open the loop. আর যদি আমি if I define f of 0 equal to 0 and f of 2 equal to 2, f is a mapping from closed interval 0, 2 থেকে r.
So this is the example you're saying, right?
F assumes every value between 0 and 2, but F is not continuous at 1 and 2.
Yes. So let's x up to 1. 3 minus x. It will start from 2.
Okay.
Yeah. Yeah, let's and I don't know, maybe it will work. But yes, so yeah, so I'll suggest to check this example in your home, because I cannot say it directly. I need some time. Yes, so please check this example.
Yes, sir.
Okay, sir. Okay.
Yeah.
Vishnu,
So we can,
let me add one point.
yes.
Actually, functions which satisfies the intermediate value property are called Darbox functions, and they need not be continuous. There are, of course, there are discontinuous Darbox functions.
Okay. Yeah. Okay. Yes. Thank you. Yes. Then we can move on, right?
Yes, sir.
Yes. So check. Written. And so we have slide number. So we need to know this concept of uniform continuity. So we say f from some a to r is said to be uniform continuous for any epsilon greater than 0 there exists delta greater than 0, where delta independent of points. Such that f of x minus f of y less than epsilon if x minus y less than delta. So this is an important concept in the continuous function. How we will see this in a geometrical way. For example, we try to take the same example, similar example what we discussed in the continuous function. So if you have a continuous function, so what the uniform continuity means that if you take any point here, like we say, for example, C here, you can find the epsilon neighborhood here. And for that epsilon neighborhood, you can find a delta neighborhood here, such that if you take any x, f of x will be inside this epsilon neighborhood. So the difference between continuity and uniform continuity is that this epsilon and this delta, this is depending on this point C. For example, if f is just a continuous function, if you choose some other point C tilde here, so and you taking the same epsilon neighborhood here, you can find a delta neighborhood here, but now this delta 1 we say, and this delta 2, this can be different. But what uniform continuity says that if you choose any point and you fix an epsilon greater than 0, and if you consider an epsilon neighborhood around that point, you can always find the same delta which is independent of that point, satisfying the continuity condition. So this is just a basic idea of uniform continuity. Yes, and there are many functions which are continuous and but not uniform continuous. So for example, you can say f from R to R, f of x equal to x square. So this is continuous but not uniformly continuous. And you can find many examples also. And in general, I would say one way to see this as like, if you have a function f, and if f have a high oscillation, for example, sine 1 by x type of function defined on 0 to 1. So if you have a function with high oscillation or high growth at some point, so for example 1 by x, at point 0 it have a very high growth, right, at a point. So this type of functions are generally not uniformly continuous. But this is not a way to identify, you need to prove it rigorously, but this is just to give you an idea, like if you saw a function and you can think about whether it's a continuous or uniformly continuous. And there is one famous theorem related to uniform continuity, which is uniform continuity theorem. But it says that let I be closed and bounded interval, and let f from I to R is continuous, then f is uniformly continuous. Basically, if your f is defined on a closed and bounded interval and f is continuous, then it's automatically uniformly continuous. Yes. So any questions, Andala? If there is no question, then we can move
Sir,
to
can
the
you explain the graph also? Or the graph for uniform continuity? You explain it, pardon? Yes. So,
this one.
yes.
So yeah, let me try to explain clearly. So for example, if you have a continuous function, then at a point C, if it's continuous, what we say, if you take a epsilon neighborhood here, you can find a delta neighborhood around the point C, such that if you take any x here, it will be in the f of C, neighborhood of f of C, epsilon neighborhood of f of C. This was the definition of continuity at a point C. So assume you have continuity at some other point, some P, and you choose the same epsilon neighborhood here. So by continuity, you can always again find a delta neighborhood here, satisfying the similar condition. But here the catch is that this delta can be different from this delta. Correct? Yes, because of we say it's only continuous. So this delta depending on this point C. But what uniform continuity says that if you choose any point and find an epsilon neighborhood, these deltas will be same. You can choose the deltas in the same at every point.
Okay, sir, I understand. This delta will be same for every case in respect of a number, C or P.
Yeah, exactly. Yes, exactly.
Okay, sir. Thank you, sir.
Yeah. Now let's try to do some problems. And I would suggest to read all the proof of the theorem which I mentioned, because if you don't understand the proof, then it will be difficult for doing the problems also. Yes, so we start with one problem, like state true or false. So the question is that suppose f defined on R to R satisfies f of x plus y is equal to f of x plus f of y for every x, y element of R. Then f is continuous at single point if and only if f is continuous on R. So what the statement says that if you have f which is continuous, which satisfies this condition, f of x plus y is equal to f of x plus f of y, then what the theorem says that f is continuous at a single point if and only f is continuous on whole R. So the question is that whether this statement is true or false. So any idea how to do this type of problem? True. So what will be what would be the reasoning why it can be true? Because if you get any problem, or what you need to do is that, like, just try the information is what the information is given. So try to write all the information which is given here. So the first information is that f of x, you have this identity, and one statement is true, because if f is continuous on R, then f is continuous at a single point also. So the challenge is that we need to check if f is continuous at a single point, then if f is continuous on R or not. So assume f is continuous at a point at, for example, C. Then we have the information for any epsilon greater than 0, f of x minus f of c, there exists a delta greater than 0, such that if x minus c less than delta. So these are the given information. So can you find some more information from these properties? At least,
Since you choose C belongs to R is arbitrary, so it's have to be is continuous on R.
no, we are assuming f is continuous at a particular c in R. So we have this result. Now we need to prove f is continuous in whole R. So just from this relation, you can get many informations actually.
F of x
Yes.
mod of f of x minus f of c. You have the f of function f of x plus y equals f of x minus plus f of y. I mean,
Can you
conclude something, please?
Sorry, can you say it a little slower? So you are saying, like, f of x you can bound by f of c plus some epsilon.
Yes. Something
Yes.
like this. Can we conclude something from?
Yeah, this is one information, but yeah, if we need it, we will use this information. But what I'm saying is that from this relation only.
Sir, we can show that f of x is equal to x into f of 1.
F of x equal to x into f of 1, you mean?
Yes, sir.
Is it true? how we get this? So how you get this information?
Sir, for f of 0, it is 0.
F of 0, it will be 0, because you can write f of 0 equal to f of 0 plus 0, and f of 0 plus f of 0. So this will imply f of 0 is equal to 0. Yes.
And sir, for positive integer, for
Yes.
any n positive integer n, then f of n is n into f of 1.
Yes, n into f of 1. Yeah. Yes.
And similarly, for negative integers, we can show that f of minus n is minus n into f of 1.
So 1 second. So f of 0 is x plus minus x. So this you will get as f of x plus f of minus x. So from here, you can conclude f of minus x equal to minus f of x, right? So
Yes, sir.
f of minus n is equal to minus f into this one, right? Or the other one?
Yes, sir.
Yeah. Yes.
And for rational numbers, we can write a rational number r like p by q.
Mm-hmm.
And sir, then I am starting with like f of p. F of p is equal to p into f of 1.
Yes. F of how you will write this one?
Sir, I am starting with f of p.
Yeah, f of p that we discussed. So it will
P
be into f of
p
1.
into f of 1, and we can write f of p as qr. In f of qr, we can write f of qr is equal to p into f of 1.
F of q.
R. I am assuming p by q as r.
P, okay. So f of qr is equal to p into f
F
of 1.
of 1. And
Yeah.
then we can write q of f of r. Q into f of r is equal to p into f of 1.
Q into f of r is equal to
P into f of 1.
f of 1.
And then f of p by q is equal to p by q into f of 1.
And 1 second. So f of r is equal to your p by q into f of 1. Yes. Yes. So you can, yeah, then what will be the next step?
So then for irrational numbers, we can, for any irrational number x belongs to R, we can
Yeah.
we can find a sequence of rational numbers xn that converges to x,
Yes.
and
Yes.
then f of x will be limit of n tends to infinity f of xn, and we know
This
that if
may not be true, because
sir,
why? Because we don't know if it's continuous or not. We only know if it's continuous at a single point. You get my point. So if you want to pass the limit, you need to know that f is continuous, right?
yes, sir, then can I do it for that point, that point, like that
Yeah.
single
For
point?
yes. So yeah, that you can do. So for example, if yn converges to that single point, so limit yn converges to f of yn. Yes. But what I would say is that the idea is good, but this we can use to prove like f have the form a into some x. But before that, we need to show f is continuous. because then everything will follow by what you're saying actually. So the difficulty here is that exactly this is what we need to do. Like we need to pass the limit n goes to infinity f of xn to prove at each irrational point. But to pass this limit, we need the continuity of f. So that was our aim actually, to prove the continuity of f. You get my point?
Yes, sir.
Yes, but it's a good idea, I would say. But we can do it even simpler to prove f of f is continuous. So what we need to do is that, like, if for example x, for example, if epsilon greater than 0, if we have f of x the x is a delta greater than 0, f of x minus f of d less than epsilon if x minus d less than delta. So if we have this condition for any x d in R, then we can conclude f is continuous, right? So this is the basic definition of continuity. So now let's look like what will be this x minus d less than delta. How you can rewrite this. So you know that f is where it is. Yeah, f is continuous at a point C. So we have this information. We have this information. For any epsilon greater than 0, f of x minus f of c less than epsilon if x minus c less than delta. So if x minus c delta, x minus d less than delta, we can just add and subtract c here. For example, x minus d plus c minus c less than delta. So if this is true, right? And this we can consider as a single point. So now what I'm saying is that if this is less than delta, then f of x minus d plus c minus f of c less than epsilon, right? By our assumption that f is continuous at a point C. So if x minus c less than delta, then f of x minus f of c less than epsilon. So x minus d plus c minus c less than delta. So f of x minus d plus c minus f of c less than epsilon. Now you can use the property of f here. So what we have here, f of x minus f of d plus f of c minus f of c less than epsilon. Because from this property, f of x plus y, we can write as f of x plus f of y. So f of x minus d plus c, we can write like this. Now you just simplify because f of c minus f of c here. So this will give f of x minus f of d less than epsilon. So at the end, what we get? So we get if x minus d less than delta, that implies f of x minus f of d less than epsilon. Basically means f is continuous.
So can you
And
show me the upper part, please?
Sorry?
Upper page, the upper portion of the page.
Here. So this so another thing I would say, like you can prove prove if f of x plus y is equal to f of x plus f of y and f is continuous, then f of x have the form some mx for some m element of R. So from this result, you will get, you can prove this result if you have this special structure. And for that, the same idea which we were discussing before, like proving for rational number, then passing the limit. So this will work to prove this statement.
Sir, in the above f of above step, f of q are equal f of q. So no. Yes, sir. F of q are equal to p into f of 1. Next step,
Yes.
q into f of 4 outside f of p.
Okay. Yes. So how do you get this? Yes, because it will be like q is an integer, right? So f of qr means f of r plus q times, right? So this means f of r plus q times. So basically q into f of r.
I see.
Yeah.
Sir,
Yes.
sir, here we are assuming that f is continuous at C, then we are showing that f is continuous at D.
F is continuous at D can be any random point. Like for example, I'm saying x and D will be any point satisfying this condition. So x and D are some general points. So you can prove it for any point D.
But sir, here it is given that f is continuous at C. Na?
Yeah, if it's continuous at C. So what I'm saying is that from the beginning, like we have this result only. If x minus C less than delta, then f of x minus f of C less than epsilon, right? So now what we're proving is that like if x minus, so now what we're proving is that if x minus D less than delta, then we prove f of x minus f of D less than epsilon.
Yes,
So
sir, I
this,
got it now.
yeah, so this implies that f is continuous at D also, and this D is some random point, so any point in R.
Yes.
So it is continuous at whole R. Any other questions? So try to complete the proof of this statement also from home. And you can find similar type of problems, like for example, f of xy, f of x into f of y, then what will be the general structure of f, this type of question. So try to do the similar problems, because I at least I know this type of problems repeats in many exams, these functional inequalities. Okay, so let's move to new problem. So again, like state true or false. F from I to R be continuous, and xm be a Cauchy sequence. Then f of xn is Cauchy. This is a statement. So for consider I is an interval. Okay. So what will be the answer to this question? Is it true or false? Like, so the statement is that like f is a continuous function and xn is a Cauchy sequence. Then the question is that f of xn is another sequence, and is it a Cauchy or not?
False.
I'm getting some true and false. So if it is false, then you must provide a counterexample. Or if it is
So f
true,
of x equal to 1 by x. Equal to 1 by
on
x. In 0,
on
comma, open interval 0, comma 1.
okay,
If it's continuous and 0, comma 1. Okay.
yes,
Here is sequence second 1 by n xn.
yes, exactly.
Converge.
So here, yeah, that's true, exactly. So the statement is actually false because you consider this function f of x equal to 1 by x on open interval 0 to 1 and consider the sequence xn equal to 1 by n. So you know that xn converges to 0, right? As n goes to infinity. What will be the f of xn will do? F of xn will be 1 by n. So it's equal to n, which is diverges. So since f of xn is diverging, so it's not Cauchy. Any questions? Or I can ask some other questions. So what can you, how can you make some changes in this structure of the function or the domain so that the statement is true? How can you do that?
So closed interval. I use
Yeah.
a closed interval.
So exactly. So if f is defined from a closed interval AB to R, then the statement is true. If you take some open interval, then you can always find some counterexample, which is f of xn is not Cauchy. Is any questions?
Sir, can you please show the previous question once more?
Previous question, the statement of the question, right?
Yes, yes.
This one, right?
No, no, the current.
Oh, the current statement, right?
Okay, sir, thank you.
Yeah. Okay, so now let's move to the other question. So again, it's a true or false question. If f from R to R is a continuous function with the property limit x going to infinity f of x equal to 1, also limit x going to minus infinity f of x equal to 1, then f is uniformly continuous. This is a statement. So what it says that you have a continuous function and you know both the limit exists at infinity and minus infinity, and that is equal to 1. Then this function is uniformly continuous or not. Yes, it's true But how we do this, how we prove this statement, basically. So let's simplify the question one more. So consider f from 0 to infinity and 0 to infinity to r, and limit x going to infinity f of x is equal to 1. So think about this problem. If you can do this, you can do the other one also. So what are the information given? So it's given that limit x going to infinity f of x equal to 1, right? So from here, you can find for any epsilon greater than 0, there exists a large number m such that f of x minus 1 less than epsilon if x greater than or equal to m. So this was the definition of limit x going to infinity f of x. I hope you are familiar with this definition. Yes, and what we need to prove here. So we need to prove for any epsilon greater than 0, any there exists delta greater than 0 for any x comma y in R, and x minus y less than delta implies f of x minus f of y less than epsilon. The definition of uniform continuity. So what can you say about the uniform continuity function? When a function can be uniform continuous? Anyone?
Same delta for every epsilon.
Yes, but actually we can use one theorem here. So for example, like we know if f is defined on a closed and bounded interval, then f is uniformly continuous, right? This we know. Now consider your restriction of f on 0 to m. So since f is restricted on 0 to m, you know f is uniformly continuous on 0 to m. Means for any xy you take from 0 to m, and for any epsilon greater than 0, you can find a delta greater than 0 such that f of x minus f of y less than epsilon if x minus y less than delta. So what we do is that we just divide this interval 0 to infinity by two way. So 0 to infinity. So we consider from 0 to m and m to infinity. For 0 to m, we can find always one general delta for any epsilon satisfying this condition, right? And after m, we know we have one condition here. Because of the information limit x goes to infinity, f of x equal to 1. So can you get some information from here to prove the uniform continuity? I mean, like from this definition, can you get something like this?
Yes, sir. For equals to m, x is equals to m.
Yeah,
Then
yeah.
m1 is equal to.
That you mean like what happens if x is equal to m, right? Or
Yes, sir.
yeah, that will be the third case that we will address after. So now consider x is between 0 to m and after 0 to m to infinity. Then we will talk about what happens at x equal to m also. So my question again, like from this condition, can you get a condition similar to uniform continuity? I mean, I want f of x minus f of y less than epsilon if x minus y less than delta for any xy, sorry, for any xy greater than m. So look at here one more time. So we have this information, right? And we need f of x minus f of y. So what we can do is that f of x minus y, we can add and subtract 1 here. So this you can write as f of x minus 1 plus 1 f of. So this will be less than or equal to f of x minus 1 plus f of y minus 1. This is okay, right? I just add and subtract plus and minus 1. So what we looking is that we looking f of x minus f of y. So this is equal to this, and we get this. And now we can use this condition. Limit x going to infinity, f of x equal to 1. So we know that if x is greater than m, we have this is epsilon and this is epsilon. Or for more convenient, we can choose here epsilon by 2. I hope this is not a problem for anyone. And if you choose like that, we get epsilon by 2, and the whole will be less than epsilon. So what I'm saying is that if you have x and y greater than or equal to m, then we have f of x minus f of y less than epsilon. So is this okay up to now? Because this is not an easy question, I would say, but yeah. So and then what we have now, so if xy between 0 to m, or if xy between m to infinity, then if x minus y less than delta implies f of x minus f of y less than epsilon. This we have. Now the only thing remaining is that what happens if x is between 0 to m and y is between m to infinity. So you can do this in many ways, like so one way I would say, like you can use the continuity definition at the point m. So f of x minus f of m, we have f is continuous at m. So we can use this x minus m, this definition, and get a similar result like this by adding and subtracting f of y. And another method you can go for is that instead of taking 0 to m, consider the interval 0 to m plus 1. And in this interval also, f is uniformly continuous, and you can just find a delta there, and that will also fix the uniform continuity. So I'll not go into the details of this, but this is, I would say, this is easy to manage. You just add and subtract the f of y here, and you will get similar result. So you can conclude if x minus y less than delta, this implies f of x minus f of y less than delta. For proving the uniform continuity. Any questions? And one thing I want to say, this was one of the questions from PA CAM interview for integrated PhD. Any questions? So we have
Your last proof.
last proof from this, you mean?
By
So I
adding
mean,
and
like,
subtracting one.
oh, here you mean?
No, sir. Last. Yeah. How you know? How want to proceed?
So from here, yeah, forget about the second method. So if x, now the condition says if x is between 0 m and y is between m to infinity, and you know that this condition, because f is continuous at m.
Okay, sir. F of adding f of m in between.
Yeah. So if you have f of x minus f of y, you can just again do f of x minus f of m plus f of m. Yeah, by this method, I would say.
Okay, sir.
You can proceed by this, and this you can choose by epsilon by 2, and this you can choose by epsilon by 2, and you can find a delta. But try to finish this proof. Yes. So how much time I have? Yes. One small problem. So again, state true or false. Let f from R to R is continuous function if range of f is subset of rational number, then f is constant. So what can be the answer, whether it's true or false? So you given that f is a continuous function and range of f is rational number. Yes. it is true, but how can you prove? What will be the idea of behind the proof?
Sir,
So
by
intermediate.
intermediate value theorem.
Yeah, exactly. So we use intermediate value theorem. I just write it as IVT. So how we prove that, for those who don't know the proof, so assume f is not constant. Then you can find x1, there exists x0 and y0 such that f of x0 not equal to f of y0. So without loss of regularity, assume f of x0 less than f of y0. So you can always find a number because one is lesser than the other. So you can always find a number k. Let's say k in R such that k not in R. So this is two irrational number, right? Because range, this is two rational numbers, right? Because range of f is in Q. So we know that between every rational number, you can always find a irrational number. So there exists a k is in irrational numbers such that f of x0 less than k less than f of y0. And we know f is continuous. Then by intermediate value theorem, there exists a number c between x0 and y0 such that f of c is equal to k. And we know that k is from irrational. So this means this contradicts the fact range of f is q. So this is a contradiction. So the statement is true. F must be a constant function. So the whole statement is true. Yes, and I'll discuss one more question, and we will do it a little bit faster. So the question is that, again, state true or false. There exists a continuous function f from R to R such that the property f of x is rational if and only if f of x plus 1 is irrational. So this is the statement. F is a continuous function, and what it's saying is that if f of x is in rational, then f of x plus 1 is in irrational. How you will do that? So anyone have any idea how to proceed? So I'll not talk about the whole proof, but I can give you the sketch of proof how to. False. I got one answer. It can be false. So can you give me a counter example? No, I mean like the proof for this is false, right? So there does not exist a function like that. How you will proceed? And so the idea is that like you define a new function g of x, which is f of x plus 1 minus f of x, And this is, this is an irrational number.
Yes.
And this is rational number. If f of x is rational, then f of x plus 1 is irrational. In the other way, if f of x is irrational, then f of x plus 1 must be rational. So difference between a rational and irrational will be always irrational. So you will get range of G will be in Q complement. So in other words, you can prove that a G is a constant function by the same way we proved the last theorem. So basically we get f of x plus 1 minus f of x is a constant. We say some number a. Now consider f of x plus 2 minus f of x. What it is? So this is f of x plus 2 minus f of x plus 1 plus f of x plus 1 minus f of x. And this will be a because g is a constant function, and this is also a. So we get this as 2a. And we know the range of g is in Q complement, so 2a also element of Q complement. This we got, right? So I'll do it a little faster. So now assume there exists a x naught in R such that f of x naught is in Q. So what it imply? It imply f of x naught plus 1 is element of irrational. What this says? This says f of x naught plus 1 is element of Q, rational. So here you got f of x naught plus 2 is from rational minus f of x naught also from rational. So the difference between two rational functions will be rational. Now we got a counter error. Because here we prove for any x, f of x plus 2 minus f of x is a irrational number. And here we got an x naught such that f of x naught plus 2 minus f of x naught is rational, which is a contradiction. So there does not exist such function, such continuous functions. I done it little faster, but these are the idea of proof. Try to fill the gap if you not understand any steps. So I would like to finish the class here now, and any questions until now?
Sir, how gx belongs to Q complement irrational number? Please repeat again.
Because so gx I defined as this f of x plus 1 minus f of x. Okay. Now assume your f of x is in Q. So f of x plus 1 is in Q complement, right? So a irrational number minus a rational number, that will be always a irrational number. Now the other way. Now assume f of x is in Q complement. So f of x plus 1 must be in Q, rational number.
Q.
Yeah. So this will be rational and this will be irrational. So again, you will get a number in Q complement.
Okay, sir.
Yeah. Any other questions? If no, I can switch to the other camera.
Okay. Thank you, Vishnu, for this wonderful session with a lot of interactions.
Thank you.
Yeah. Now let us go for an interaction with students. Dear students, now it is a time for you. You can ask any doubts regarding the class, or you can make the comments about the class. Yes.
Hello, sir.
Yes.
I am Subha Kundu and come from West Bengal. Class is very nice and
Thank you.
lot of information you get. So thank you, sir.
Thank you.
Thank you. Yeah. Thank you, Subra Kundu. Others?
Sir, can I get whole recorded class?
Yeah, of course, we will share it. We will share the YouTube recording.
Okay, sir. Thank you, sir. Thank you.
Hello, sir.
Yes, Dia.
Hello, sir. I
Hello.
am Dia. I am also from West Bengal. Sir, the class is very nice, and I like the interactions, sir. You have explained your every step to us.
Yeah.
It's very nice, sir.
Yeah. Thank you.
Thank you, Dia. Others?
Hello, sir.
Hello.
I'm Shikha. I'm a second year MSc student. I'm from BIT Mishra, Jharkhand. Yeah, the session was really very good. You explained each and every concept in a very great manner. It was very easy to understand. And sir, I want to know that how to clear the TIFR exam for PhD. Any tips, tricks, something, how you did?
Like for me, like I was mainly focused on these three courses, like real analysis and algebra group theories mainly, and linear algebra. At that time, I was sure like these three. If you know basics of these three subjects, then it's easy to get there at least. But now I know I don't know how the syllabus is it changed or not. Like yeah, but these are the three important subject I would say you should give most preference for these three topics.
So real, linear, and abstract. Algebra.
Abstract, yes. Exactly.
Okay. And so what about the interview part?
The interviews, like they'll start with some small questions, like I don't remember exactly what were the question. That one was this this question, I think, like the range of a function is in Q complement, then what will be the function, like f is constant or not. So that was one question, and then they start increasing the hardness of the question. So one of the question was that the one I discussed, like if limit of a continuous function is finite, then whether it's a uniform continuous or not. So at the end, like they what I understood is that they will not expect like you should do all the proof and theorems with details. At least try to do the problem, and if you stuck somewhere, they will try to give the hints. And the main idea is that like if you can catch the hint, that's a good positive, I would say. Because research is like that, right? There will be supervisor, he will give you some hint and you do the research yourself. So I think they will look for that mainly. And in my interview, like there was 5 or 6 questions from this real analysis part, and 1 question from group or ring, and one from linear algebra. 2 from linear algebra, I would say. Yeah, it was like, and it was very, very long also, like around more than 1 hour it took for the interview. Yeah.
Okay. And so, what all are the opportunities in abroad for?
Like I said, like in abroad, if you want to apply for PhD, at least in Europe, what they mainly consider is their master thesis, not about your mark or anything. Like if you have a good master thesis, like that will be a great plus. And I don't think they will much care about your marks and everything. Yes, so try to do some good master thesis, and also you can do these summer research programs also. And also I want to mention, like in some countries like France and everywhere, there are some advanced masters, like 1-year masters, so that you can get with the scholarship also. So it's like you can do the 1-year masters and 3-year PhD there. So I would say this is also better than doing a 5-year PhD in India, and it will be quite advanced also with masters. Yes.
Thank you, sir.
Thank you.
It was really nice. Thank you, Vinod, sir, for organizing such beautiful sessions.
Okay, thank you, Sikha. Others?
Hello, sir.
Hi.
I'm Hannah Matthews, currently studying 3rd year BSc Maths, Marthoma College, Chungatra. I'd like to thank you for taking this class for us to patiently solve all our doubts. Thank you, sir.
Thank you.
Thank you, Alina. Others?
Hello, sir.
Hello.
Yes.
I'm Gayatri. I have studied in Karanda House College, Delhi. It was a very nice class, and you have explained everything so clearly, so it was easy to understand. Thank you, sir, for
Thank
such
you.
a wonderful class. Thank you.
Yeah, and sorry, I messed up at some points, and yeah, hope it will be okay.
Thank you, Gayatri. Others?
Sir, give any reference for real analysis book.
Like for me, I studied this Bartle and Shepard Introduction to Real Analysis. So I think I did not read any other book, but I was doing all the exercise problems from that book. So at least for TFR, I know that will be enough that time. Yeah, if you do all the problems from that book. Yes.
Of course, there is a book by Kumar and Ajit Kumar on real analysis. That is also a good one with lots of problems.
Yes. The important thing is that you must do the problems maximum as possible. That's, yeah.
Thank you, sir.
Thank you.
Others?
Hello, sir. I'm
Hello.
Nishita Pendharkar from Maharashtra. Thank you for today's session, sir.
Thank you.
Thank you, Nishita.
Thank you, sir, for today's wonderful session. It's nice. Thank you, sir.
Thank you.
Yeah, Amo, please introduce yourself.
I'm doing my MS.
Sorry.
Yeah, some network issues there.
Okay, yeah. No problem.
Okay. Okay, if any others? Okay, you can ask anything regarding higher studies about TAFR or opportunities doing PhD abroad. So feel free to ask. Is Anamika?
Sir, hello, sir. I'm Anamika from Zamunis Puraipan College, Kerala. Sir, wonderful session, sir. And I'm currently a third year student. A wonderful session, and you provide an opportunity everyone to discuss the questions and to think about that. Thank you, sir, for this nice session, and thank you, Vinod, sir, for arranging this session.
Thank you.
Thank you, Anamika. Anu, yes, Anu. You good? Okay, if any of you would like to ask anything regarding this class or higher study opportunities, you can do it now. Otherwise, yeah. Yes. Some question in the chat box.
So research proposal, like for me, like in masters, I did not done any master thesis while doing the MSc, and research proposal I mainly discuss, like I check what are the what is the PhD position and what is the research topic. So I mentioned, like I took the courses which are related to that topic, and yeah, I don't remember what exactly I written, but it's mainly like what you know about the topic and what you can do with this topic, like that. Yes. I don't remember exactly how it was. So what I think is that if you have a master thesis, then try to explain the research what you've done and what you can do from what are the future problems you can generate from that thesis and this type of things. So this will give a good impression to you if you can find some.
Yeah, that will be more better, because starting from a completely different problem and writing something on that may not be that much attractive. It will be better to some further works, that continuation with the MSc dissertation, that will be more better, right? Okay, any others? Okay, I think we can wind up here. Thank you, Vishnu, for being with us. And,
Thank
I
you.
wish you all the success in your research and academic career. Once again, I would like to thank all the participants for being in this session throughout, actively involving in the discussions. Thank you, everyone.
Thank you. Bye.